Question says a typical truss with loads acting on it and the sketch which is not drawn to the scale. You have to find the reactions RL and RR and determine the magnitude and nature of the members of the truss by completing the table given on the table that is given below. So as you know, the first step is you have to do boards notation using capital letters in clockwise direction. Also label in between the triangles because every space has to be labeled. Next, your load line scale, it says 10 mm is 100 kilonewtons, so you can simplify that one. So both sides you can divide it by 10, so you will get 1 mm is equal to 10 kilonewtons. This means whatever force is given on the trusses there will be divided by 10. Like 900, when you divide it by 10 you will get 90, and 400 when you divide it by 10 you will get 40. Right, so A to B is 900, 900 divided by 10 is 90. So from A to B on your load line you are going to measure 90 mm, and then B to C is 400, so 400 divided by 10 will be 40. So from B to C you are going to measure 40 on your load line. Right, that's 90 and this one is 40. Now you can complete your polar diagram by joining all the points to point O. You can draw the arrows, label it as A0, B0, C0, and at the same time you can also label the diagram as a polar diagram. Right, so you're going to take all the lines straight down from RL 900 kilonewtons, 400 kilonewtons and RR. Then you take it parallel to A0. A0 is between RL to 900, so you're going to transfer it in that space. Right, so A0 is going to go there. B0 is going to go from 900 to 400 kilonewtons, that's the space for B0. And if you look at C0, it's from 400 to RR, so this means your C0 is going to remain outside. Right, that's your A0, this is B0, and you can transfer your C0 which is from 400 to RR, that will be outside. Right, so if you want to close your funicular polygon, you know it's from RL to RR. So if you look at RL, the starting point, and RR, the ending point, so you have to join those two. Don't have to worry about the point C0 that is outside, because you have to only join it from RR to RL. So D0, our closer, is from RL to RR. Just like what you have done in the previous exercise. Label it as D0 closer, and you can transfer this distance on your polar diagram. You can also label the diagram as funicular polygon. The diagram is your polar diagram. So that's how you're going to transfer your D0, your closer, back to the polar diagram, and after that you will be able to find your RL and the reactions RR. Right, that's your D0 already there. Take it parallel to that and transfer it there. Now if you look at your RL, it is from D to I. So you measure I to D. Whatever distance you are going to get, you are going to multiply by 10, because your scale is 1 mm is 10 kilonewtons. So if you, let's say, get 10 mm, then 10 times 10 will become 100. Likewise, if you get 5 mm, so 5 times 10 will become 50. Every mm that you measure there is to multiply it with 10. So that is coming somewhere around 661. So 61, when you multiply it by 10, you're going to get 610 kilonewtons. And if you look at your RR, right, your RL was 61. So 61 times 10, since your scale is 1 mm is 10 kN. You'll get 610 kilonewtons. That is the value for RL. You can measure your RR. That is coming somewhere around 69 mm. So 69 times 10 is going to give you 690 kilonewtons. So RL is around 610 kilonewtons and RR is 690 kilonewtons. Then if you make 1 mm error in this question, your answer will differ by 10 kilonewtons. So you try to be as precise as possible. Right, so now you can check whether the answer is correct or no. You can measure or you can add RL and RR. The total is 1300. The total of the forces 900 and 400 is also 1300. So they are matching, because the forces that are acting downwards should be equal to the forces that is acting upwards. Right, so now we're going to draw a force diagram there. We already have A, B, C and D. We are left with E and F. So to locate E, we have to take I to E and draw a line from I. And to get the intersection, we'll take B to E, the member BE. From B, we'll draw another line, and where they will intersect, that will be your point E. Right, so that's the intersection there, that is your point E. Now we are going to locate point F. I'm going to experience an interesting case here. So if you look at, oh, snack time. Right, if you want to locate F, C to F is a vertical line which is already there. from C there's a vertical line that is going, and D to F is a horizontal line. So you can see C to F, the vertical line is already drawn there, so we don't have to draw that line. Now we take D to F, and when you draw a line at D, right, that is the line that I've drawn at D. Your intersection is on the load line. That's your D to F, and your C to F is a vertical line. So the vertical line is already there, so those two lines are meeting exactly where your point D is. So this means your point D and F lie on the same place. Now I will join E to F because E to F is also a member, and now I'm going to check whether my diagram is correct or no. So I'll take it parallel to EF from the truss, space diagram there, take it down, and it should be exactly in line. This means your force diagram is correct. Now the distance AE, BE, CF, DF and EF, you can fill it up. You measure A to E, whatever answer you get, you multiply it by 10 and write the answer there. Right, so in this case, if I am getting it, let's say 94 mm, so 94 times 10 is going to give me 940 kilonewtons. Because every mm that I measure there is equal to 10 kilonewtons, so I have to multiply by 10. So that is 940 kilonewtons. You can write down kilonewtons in magnitude column so that you don't have to write in all the specials that is there. Now I can measure your B to E. And fill it up all whatever lines you want. If you measure D to F is a single point, so D to F will be equal to 0. Right, so when it's lying on the same point is 0. You can measure E to F, write down your answer there, and you can also measure B to E. Nature. So you have to do the joint analysis. So you have to start with the first joint, that's our J1. And you can make a rough sketch of that. Label the letters as it is in the diagram there, A, E, F and D. And then you have to move in clockwise directions. So we don't have to look at RL because the arrow is already there, so we'll start with A to E if you go clockwise. So when you look at the diagram, A to E is coming downwards. This means you have to make an arrow that will be pointing downwards near the joint there. Then E to F is going upwards, so here it will be going upwards, and then E to D or F to D is just a single point, so you just put across there. You can't find any arrows for a point. So when you see that your magnitude for any of the member is 0, that member is called redundant. This means even if I remove that member, the structure is still going to be stable, because that member does not carry any force. Right, that's what tension and compression looks like. Tension is same as tie, compression is same as strut, and if you have 0 kilonewtons, it should be redundant. That's something new you're going to learn in this worksheet. Right, so you can transfer the arrows and label it as compression or tension. So E2 is compression because the arrows are pointing outwards. E2F is tension because the arrows are pointing inwards. And F2D will be redundant because the force there is 0 kN. We cannot find any direction there. So you can fill that up. Write down C there, and there you can write down T for E to F. Now we are left with B to E and C to F. Right, so BE CF. So that is joined. Right, BE and CF. That is the joint we have to look at because that is connecting both the members there. So you make another joint. Do the above notation there. Right, F2 is already a arrow there. You can see you don't have to do that. You look at E to B. See here you don't have to look at the table. Table says B to E, but here if you follow the clockwise direction it says E to B. So you have to follow what your joint analysis is saying. E to B, this means we are going from E to B, and that is pointing towards the joint. And the next one is C to F. So if you look at C to F, it's going upwards. So you can transfer those also on the truss there in the space diagram, and both is coming to compression because the arrows are pointing outside or outwards. So C and C.